Now give the next talk from Bell Labs.
Okay. Thank you, Richard. And thank you for the invitation to this workshop. So I'm going to talk about my department here in Murray Hill at Bell Labs, but I'll start with a little background, a little bit of history, which may be relevant to the NIM's interest in developing a stronger applied mathematics effort in South Korea. And then I'll tell you a little bit more about what we do nowadays, give some examples of recent work, and if at the end there is time, I'll even talk a little bit about some of our recent research towards the end. So actually Bell Labs hired its first mathematician in 1916. And interestingly enough, that was before Bell Labs was established. Bell Labs was established in mid-20s. But the first mathematician was hired in Western Electric, which was the manufacturing arm of AT&T in the mid-1910s. The name of the individual was Thornton Fry, and he was hired by this guy Harold Black, who was a physicist. He was an experimental physicist, and he actually had gone out of his way to hire a mathematician than an engineer, and there was a reason for that. I couldn't find a picture of Thornton Fry. I Googled him all over the place. So here's a picture of one of the reports he wrote. Potential theory. So he had observed that the engineers had problems of transmission. They wanted to understand transmission of waves in copper wire, and these were differential equations, and they needed some help in understanding the sophisticated models that they had to deal with. So that's why he'd gone to the mathematics community, and the same problem existed with switching. When you were switching, you wanted the switches to be non-blocking or rearrangeably non-blocking, or blocking to a certain extent, and you wanted the switchboards to operate a certain amount of load, and engineers were not familiar with these. These were either applied probability models or wave equation models, and these were not historically taught in engineering. So he reached out to the math community by hiring Thornton Fry, who turned out to be a really, really good choice. And I'll explain to you why. So his success resulted in the creation of the first mathematics department. It may be, my colleague in IBM may know this, but it may be the first mathematics in industry group in the US. I'm not entirely sure, but this may be. IBM might have something. But. So what was it that... so Fry, after about 10 years of heading this department, wrote an article. It's called Industrial Mathematics. And I don't know if the SIAM team who wrote the 2012 report looked at it, but it's really good reading. It's actually, I read it one more time. My boss had told me about it some time ago. You know it? Yeah, it's many topics that came up this morning are explicitly explored and discussed here in this. I'll give you a few examples of that. So Fry's ideal mathematician for industry would be needed because of her or his greater confidence in conclusions than experimental results have. So you can say with certainty because you actually prove something that it's true. For Fry, the other key advantage was the logical way of thinking that mathematicians brought to the discussion. Again, we heard this morning. And the clarity, taking a problem and clearing it up from all the clutter that typically surrounds it, especially in an applied setting. And the desire for generality so that the results could be reused as opposed to, here's the solution to one specific problem, tomorrow's problem is different, so we're going to do something else. General methodology which you can apply and reuse over and over. So these are in the article. So if you read it the first few pages, he comes to this conclusion. But there is more. These are his expectations of the mathematician. They should be interested in practical matters. Okay? He calls it, these are his words, they need to be gregarious and sympathetic. What he means is that they should not hide in their offices. We heard this also this morning. He says that they have to be cooperative and unselfish. And what he means is that often the mathematicians in industry would play the role of a consultant, and a consultant cannot compete with people who hire him for the attention of the higher management and stuff like that. So Fry was very sensitive to the fact that his team were being a resource across the corporation, and he didn't want the resource to be seen to be a destructive force. And finally, he says, he numbers these 1, 2, 3, and 4, and says, fourth, they need to be versatile, because problems change. In academia, there's interest to dig deeper and deeper and deeper, and sometimes a decade could go by and one hasn't moved on to something else. Well, that happens in industry too. Actually, I've seen that. But more often the problems change, and once the problems change, the mathematician hired needs to be able to make that shift, move into a new area, explore new questions. So anyway, these are some thoughts of the first, or approximately the first math group that was created in industry. And we see that 70 years later, 73 years later, they're still as valid as they were back then. So these are, in some sense, universal truths. Now, he also talks about the training that the mathematicians should have, and this is very different. This is where the Siam group will see a big difference. In those days, there was no such thing as at least explicitly as an applied math program anywhere. He's really talking about people who were trained in what we call today pure math. So he stipulates that these guys need to know about determinants, they need to do X, they need to be able to use bicircular coordinates, they need to be able, all those things that electrical engineers were trying to do. And so anyway, these are big differences between this report and what we have 70 years later. There's been a tremendous shift towards applied mathematics, both in industry and academia and industry, and that's a big difference. And institutions like IMA and NIMS are there in order to take advantage of that, but also broaden this interest. Okay, so this was a little bit background to that. So he actually applied two rules in his department. He let their mathematicians have their own research program. This is something that we still do, which is probably very rare in industry. And it's an uphill battle, I can tell you that. And people who have to negotiate a budget every year with higher management know that also. But to Fry, this was absolutely important then, that each mathematician in industry pursues an independent research program. Okay? But at the same time, they had to be available as consultants to solve solutions, provide solutions to problems that people had in the corporation. So in his view, the ideal employee would combine these two. And this bought him a lot. This emphasis on having each mathematician have their own research. And today we have it in the form of 50-50. Everybody in the department spends 50% of their time on their research and 50% on something practical. Now, sometimes it's very hard to keep this exactly at 50-50. In some cases, it becomes 65-70% in some years, for some cases. But overall, this has to be balanced, and that's really a management challenge, to keep that balance. Because if they go in their own research direction, within half a dozen years, I'm sure, you can imagine that department will disappear unceremoniously from the scene. Nobody would be interested in seeing it. At the same time, if they focus purely on the shorter term problems, they lose contact with the research community. So the tools and techniques that are available, and these are advancing more rapidly now than they did in 1940s, that's very important to keep in touch with the community that is doing the research. So that's really the motivation. So it's a hard thing to do. We try it. Now, just for your information, at the time that Fry wrote this article, to the best of anybody's ability, there were no more than 200 mathematicians in the US working in industry. And this article actually painstakingly goes through how he arrived at this estimate. And that includes statisticians and actuarians. So far fewer would be doing, say, PDEs or solving applied probability problems there. As a later head of the math center at Bell Labs said, and this was around the time when Bell Labs was at its peak in terms of both research, independent research as well as its applied work, was that our job was to stick our nose into everybody's business. Meaning, what he means to say is that we would work on any problem people care to bring us. So I'll give you a sample of early problems from the 1930s all the way to late 50s, 60s. It's just a sample that I was able to gather. So solutions to analog transmission problems via ODEs and PDEs, we mentioned that. That's why Fry was hired to begin with. And he wrote a book, actually, on this topic. He wrote a few books. One of them was this. Applied probability models for queuing systems. Models of switching systems and networks, and interestingly enough, we still work in this. This problem doesn't seem to end. And now networks are even more important than they were in the 1940s because of Facebook and Amazon and all sorts of, and Google, not to mention others. Use of telephone relays for computing. Tracking and prediction of position of submarines, ships, and planes. Now you may ask why mathematicians in Bell Labs were interested in tracking ships and submarines. Well, there was a part of Bell Labs that worked with the US government from the 30s all the way through the 50s. So they were independently funded. Even the program were not known to the corporations in any detail, in any substantial detail for a long time. So that's why. Cryptography and communication in noisy environment. Now this communication in noisy environment is the bread and butter of mathematicians in Bell Labs. It has been, and it continues to be. And then the final, which is toward the end of the 60s, statistical computing. So this is just a flavor of what was worked on. So Fry, around 1940, around the time that he wrote that article, he actually hired a fellow, Claude Shannon, to look at this problem of communication in a noisy setting. And Shannon went on to create the Age of Information. It's all in one paper, the meaning of information, entropy, the channel capacity, and how you do efficient coding to achieve that capacity, all came out of a very practical setting of transmitting signals over a copper wire when there is noise. So it kind of justified Fry's insistence that people work on both. They have their own independent research as well as work on practical problems. Okay, so that's enough of history. So if you're interested more, there's this article. It really is, it's interesting to read. And there's this book, if you're interested in history of Bell Labs. A fellow, John Gertner, 2 years ago wrote a readable book. Unfortunately, not unfortunately, out of choice, he chose physical sciences as his emphasis. So there's not that much about math and information theory. There is a little bit, but not much. It's mostly about how the transistor was invented and so on. Okay, so this is old stuff. What do we do now? So just to give you a picture of everything other than math here, the claim, and this is actually a true claim, is that the key accomplishments have all been driven by real-world practical needs. And that's really what separates industry from academia, in that there are specific things that the industry is interested, the business is interested. And there is more sources of interesting problems here than you would imagine. I mean, people who work in industry often find that out of 20 problems that they come across, maybe there is time to explore one in any significant detail. You just have to let the other ones go. There's too many. And if you can write it down in a book somewhere, and many years later when you're retired you come back to them, maybe that's one way of doing it. I'm not sure anybody has done that successfully. It just gets forgotten. But there's a lot. And this is just the fact that if you pay attention to these practical problems, you get a lot of interesting stuff. You know, C programming language came out of the need to organize these files, these enormous files of hundreds of millions of records. And you wanted to swap columns, rearrange rows, add certain entries here and there was no programming language that was sufficiently flexible to do this. So that came out of that need, and then it went in its own independent way to create modern programming languages. Optical fibers, well, that was the need to put more bits, and copper, of course, has limit. You will see that the limit of copper is much higher than anybody thought. I'll talk about that in a little bit. And some of the more recent work are listed here also. So how is today's Bell Labs organized? Actually, we are jointly organized with something called the Chief Technology Office. The Chief Technology Office's role is to make sure that they are aware of what is happening with the focus on our businesses. What kind of routers, what kind of switches may be available, what kind of chips, and what kind of performance may be coming our way. So this is an industry roadmap, independent of what we as scientists or engineers do. That's their job. And the fact that these two are combined with Bell Labs is actually a big has been a major asset, because these organizations used to be independent. Somebody would say, such and such technology is really important, and in Bell Labs nobody would pay an iota of attention to that, because it was a separate organization. They did not have any accountability to each other. I mean, in theory they did. In practice, there could be a separation. So nowadays, a lot of high-level programs that we formulate in Bell Labs are informed by the chief technology officer's, predictions about what's coming down the pike, which is a good thing. Anyway, there's 800 of us, roughly split equally between the US and Europe. Of course, we have satellite offices. We have one in Seoul. It's not very large, it's about a dozen. Yosop, who talked earlier today, used to be there until a few months ago, and he decided to test the greener pastures of startups. But anyway, there are about, and we are spread in Stuttgart, Antwerp, Paris, and Dublin in Europe. And the other are about 400, 300 something in the US. And these are the 7 labs that we are in: computer science, math, physical technologies, optics, wireless, broadband access, software systems, energy efficiency. Now, out of these numbers 3, 4, 5, and 6 actually are aligned with businesses with similar names. We have businesses whose job is to sell wireless equipment. CDMA is still used in Korea, so I'm sure you're familiar with the Lucent CDMA product, wireless optics, and so on. Some of the other labs, like physical technologies, are primarily focused on optoelectronics. And we do have a software and systems business now. It used to be services of some sort, but now it's called software and systems. This is a very small research program, energy efficiency, but it's important to reduce the energy footprint of telecommunication, which currently is negligible, is less than 1%. However, if you extrapolate across the next 20 years, it's very large, potentially as much as 20 to 25%. Just think about the data centers, how much electricity, how much power data centers use now. And as the demand for those go up, you'll see that this is important. So I work here in this lab, and there's 20 of us in the US and 10 in France. That's a new initiative to grow the numbers in France, partly because there are lots of good mathematicians in France that used to be part of various industries, but somehow they've been dismantled. So the idea is to hire them for everybody's benefit. So our mission is to provide mathematical and principled solutions to problems. Heuristics and simulation-based stuff is still good. We're not ignoring those. But we are truly interested in formal mathematical solutions, if and when possible. Not always possible. Not always useful. Not always useful. Sometimes the heuristics that people come up with do the job, and adequately. But when the more formal approach is successful, it's really a big hit. So you can call it higher risk, higher reward type of research. And we've seen this succeed. And I give you a few examples from the past 10 years to validate this claim. And actually the validation is that we are still around. In a tight funding environment, if you're not very useful, then you don't last very long. Okay, we are the only lab which has worked with every business group. I mean, some of the other ones only work with one. If you're in the optics research lab, then naturally you only work with that business. However, we are the only part of the labs which has worked with every part of our businesses. Okay, so how is the department organized? The 5 pieces to the department: coding, theory, and practice. This is how to compress, correct, recover, and encrypt data. Straightforward, right? Stochastic networks. This is applied probability. It really comes handy when you're doing problems in resource allocation. Like you have a radio access network, you have a limited number of frequencies, a limited number of time slots, and you want to meet demand from mobiles that want to have multimedia or voice, data, this, that, and the other. And it's always a good problem in applied probability to solve these. Graph analytics, this has come in the form of big data, but for us it has a very specific meaning, which is how to do graph algorithms in a scalable manner. Simple graph algorithms, if you have anything above n squared, and if you have 100 million nodes, the whole thing grinds to a very, very unpleasant stop. So what do you do? Okay. Network economics, this is a more recent effort, and it's to do with how you leverage consumer economics and quantify technology adoption. There's lots of game theory models that we use. Our people who have been interested in our work, I have to admit, have been organizations like marketing. So this is an example. I guess in industry, mathematicians do work for marketing firms, but here I had not had much opportunity talking to them until a couple of years ago when we did some work on games. The idea is, for example, maybe in Dowgen you have 5th generation wireless already, and then suppose there is a new generation of wireless that is even faster. What is the motivation for you to adopt this new technology? Well, the question is, who are you competing? If you have no competition, if you're a monopolist, then there's absolutely no motivation. You can sit on the old technology for as long as you like. But if there is competition, then there is a trade-off here. If you wait too long, then you can just lose the market. So the question is, what is the right approach? So we wrote some reports on this, which all of a sudden, unbeknownst to us, the marketing department loved, and it was part of their presentations to our customers. So, by the way, it's not in South Korea, the wireless technology is envy of the world, so it's not the problem here. We were talking about Europe, where they don't want to migrate to four generation wireless. Last one, applied cryptography. This is a very small group, but it's very effective. And the idea is to, for those of us who are familiar with cryptography, this is 99% of the papers are completely impractical. One day they will be practical, but not yet. And so one of our staff members a few years ago thought of really doing, he said, look, there's so much work here. Got to be a way to use these. For example, if I want to query a database so that neither the database owner knows what I'm querying, nor can I get any information other than absolutely what I want to get. Is there a protocol that will guarantee that the database is not giving me more than what I appear to be asking? And he actually built it, and it works. So we are actually interested to see if anybody wants to buy this. But we are maybe a little ahead of the market. But the point is, that's why we call this applied cryptography. We are actually making things that work in this space. So some examples of these. So coding theory, compression. So I don't know what the exact situation here is in South Korea, but certainly in North America and much of the rest of the world, there's a lot of copper wires still coming to the residential customers' home. And these were designed for 64 kilobits per second. With modems, you could raise them to 1 megabit per second. With fiber to the, not to the home, but fiber to the curb, which means that you bring the fiber to within, say, half a kilometer, and then from there on you link them with the copper, and you want to get 300 megabits per second to go at a distance of 200 or 300 meters. And initially the answer seemed to be that's a hard problem or it's impossible. But it turns out that it's possible. We are now reaching 1 gigabit on copper in distances. Of course, these are short distances, but there's a lot of signal processing here. And actually, there's a lot of math. It's all to do with matrix inversion. It's one giant matrix inverter that works 4,000 tones, 4,400 by 400 matrices are being converted constantly. And that's what it takes. I'll show you in a little bit. Okay, so let's actually go to this one because I started it, and then I'll come back. All right, so copper, these are the rates. So a binder of copper is it's a thick cable with lots of twisted pairs inside, anywhere from 24 to 400 twisted pairs. And when you try to increase the rate on these in digital communication, the electromagnetic interference goes up. It goes up so fast that the noise, the environment is dominated by noise. So the signal is just swamped. Okay? So if you think about it, you have, say, 400 transmitters and 400 receivers. Electromagnetic interference is like noise. So you can think about horizontal lines as the channels that you want to have, and any line that's not horizontal is interference. For example, this transmitter creates an electromagnetic wave that affects several of the other copper wires inside that binder. So that you can represent as an arrow that goes from this input to another output, not intended. So input 1 is supposed to talk to output 1, etc. But then you have this cross input-output. Okay? So what you get is essentially, if X is your signal, H is your gain matrix, Y is the output, Y equals HX plus noise, and of course H is not a nice matrix, but you could invert H, you can feed that back into the source, and what you get is a diagonal matrix in the output, which is what you want. So each transmitter, instead of transmitting just its information, it transmits its information combined with not a random, but what looks like a random combination of signals from all other sources, so that the output is a clear signal for that output. That's, in the industry, this is called multi-input, multi-output. It's used in wireless, actually. And this is the first instance of use of MIMO inside the wire. So we were able to increase the lines from 10, 20, 30 megabits per second to 100. And now we are heading to 300 megabits per second. And the economic impact of this is huge. To delay placing fiber in the last half a kilometer by a few years is worth tens of billions of dollars to operate. So if you can make the copper work up to 300, and 300 megabits is going to take care of most of your 500 channels needs. So that will do the trick. So we actually built the first instance of this in real life. And this was the math team who did this. The first demo, and now it's part of a product that we sell. It's actually good business. The copper business was, all the charts show it that it's eventually going to zero because who needs copper? But with this, the charts have been revised. They go to zero much later, 5 to 10 years from now. And in the meantime, there is business to have. Okay, I'll tell you about one or two more examples. And how much time do I have? How much? 3 minutes? Okay. Okay, I'll give you this example. This is an example of something we worked on that was really cool, but it still is not commercial because of the dot-com bubble burst around 2000. So the idea of this device is it switches colors inside fibers. So you have waves coming in one fiber, you want to rearrange them. It's a cross connect. So you have to take, and the way it works is light, these two lines are fibers. The orange ones, here and here. So the light is reflected on an array of mirrors, and depending on what you want, where you want you want blue to go to port number 4 and green to go to port number 3, etc. So there are these micro mirrors, and there's 1,000 of them in a 2 inch by 2 inch chip. And so what's the math problem here? The non-math problem, I'm sure you can imagine what a huge challenge this is. But the math problem was to align the mirrors, train them. You have to, before you sell this product, you have to make sure that when it says, okay, here is a cross-connect map, that the mirrors align so the various input and output ports. Now if this is 1,000 by 1,000, so that's 1,000,000 different configurations. The original training required a few seconds, actually maybe up to a minute or two of training for each mirror. So that would be 1,000,000 minutes of training. And one of our colleagues took on the challenge of reducing this, and he ended up reducing it by several orders of magnitude. So initially, basically, it was not manufacturable, because if it takes you months to train this, it just wouldn't work. You can't do it. But reducing it from many months to a few minutes was a big deal. So, okay, so I think my time is up. There are more examples of these in recent years, and this is our claim. Whenever we are challenged, I have these slides ready to show that the company gets real value from math, and it works. So the message is, as long as you can manage this, you can balance the tightrope. Math is one of the greatest assets we have in the lab. Thank you.
Are there any questions?
What are some of the significant changes in Bell Labs since the mid-90s?
Many. Yeah. There are many significant changes.
How has that affected the mathematics community, its size, its work?
Yeah, that's a good question. So in the 60s and then 70s, a lot of the labs grew in the dimension of very academic type research. Because of the Nobel Prizes, people loved them. So more and more of the lab directors aligned their work to get more Nobel Prizes. So they ended up with 9, which is good, and we may get some more. However, that wasn't the right focus. So when the company from a regulated monopoly, which was AT&T in the mid-80s, migrated to a commercial entity, this pressure to do more relevant work with a shorter term impact became far more important. So, for example, the math center at some point was about 70 people. Now there's only about 20 plus 10, 30. So we are a third, maybe a half, at most a half of what we used to be. We used to have a lot of research in physics and chemistry, fundamental physics and chemistry, which we don't have anymore. However, I think of all that said, of all the basic research that we had at Bell Labs, math is the only one which is still around. And that's primarily because of the successes that I showed you.
Would you say, you talked about all the impact that the early work at Bell Labs had, not just in terms of Nobel Prizes, but as you were saying at that time, there was a lot of practical impact from that work. Would you say in the new environment where you've sort of shortened the horizon of the activity, that you're seeing more impact on actual products and sort of industry insertion than in the old Bell Labs?
Yeah, that's the goal. No, the goal is, the organization is put together so that there would be shorter, more immediate impact. However, certain things like the impact that transistors had was so phenomenal. If you have one like that every 50 years, that pays for everything. But nobody knows how to organize an industrial research lab. Yeah. Yeah, it's unknown. It's not known how you manage an organization like that. Yes, one invention would save you. Actually, AT&T had a requirement to cross-license all its inventions to the public because of its monopoly status. So they didn't make money out of it. But if they had collected a penny from every transistor, that would have been a lot of commercial value, right?
Okay, are there any other questions? Okay.
I guess to understand the Facebook books, I mean, so I guess to make copper useful again, you basically invented this matrix inverter. Does it use some kind of proprietary Bell Lab algorithm or?
Yes. If you use textbooks matrix inversion, it won't work.
And this proprietary Bell Lab algorithm, the matrix inversion algorithm would be patented, or is it like actually published, or what?
No, it's not. As far as I know, it's not published. Part of it is patented, and there may be parts of it that have not even been patented. But what did you call it?
Trade secret?
Maybe.
Yeah. Okay.
Any other questions? Okay, I'd like to make thank you very much, Raj.
Sure. Thank you.